thank you for coming. This is going to be an overview of the UALink 200G spec. We won't be getting all the way down into all the details. We'll get into a fair amount of detail, but not every detail you may ever want. The specification is available on the web with all of the details. We'll begin with an introduction. We're going to cover a little bit about how UALink came to be, what the overarching goals of the UALink consortium are, and where we're headed. You know, this is, I think, the official slide of FMS 2025, the first slide. You know, AI is eating the world. You know, it's a bottomless pit of compute and memory needs. And in order to try to meet those needs and build to these, you know, models that we need to scale, we need large amounts of compute, large amounts of memory, and those needs keep growing. What UALink is going to try to do is provide a scale-up load store model, high-speed, high-bandwidth interconnect to group up to hundreds of pods in your training systems. Now, the industry, you know, there are proprietary mechanisms and standards in this area, but the industry really needs an efficient, open standard for this sort of work, and that's what UALink is trying to be. UALink will scale to tens to hundreds of accelerators in a pod. We're going to be using standard Ethernet SerDes and PHYs at high band, you know, the 200 gig high bandwidth stuff as our base physical transport layer to get to those tens to hundreds of pods, you know, and that will work for, you know, large inference models. Can cover that in a pod in a large inference model. For really large training models or even larger inference models, you'll take a pod connected with a scale-up network and you'll string those together using standard scale-out networks like Ethernet. Okay? So we're an open industry standard controlled by a consortium with a 12-member board of directors. You know, the companies involved in the board of directors is shown here at the top. You know, this board, we represent leading hyperscalers, network and fabric providers, system providers, and silicon and IP providers. There's a very broad range of expertise, both from the use and the create side in the board, right? Something that's kind of unique about our board is a lot of the companies, several of the companies involved here are not typically involved in standards organizations, but they are here. We feel this highlights, right, the need and the importance of a technology like this to the larger AI community. Another important aspect is we are now, in under a year and a half, at 100 member companies, over 100 member companies involved in this work. Everything from test to, you know, users to IP providers to software, you know, and some of those names you can see here on the bottom of this slide. So let's talk about the timeline. You know, in May of 2024, there was a press release announcing the promoter companies and the 12 promoter companies as the base. In October of that year, 2024, we posted, you know, we opened it up to member companies. We then had the first specification go out on April 8th of this year. So we went from start to a completed 1.0 specification in under a year. We went from 12 member companies in October of 2024 to 100 plus companies, you know, today in under a year. So this has grown very rapidly. And, you know, we feel, you know, we're going to be able, the goal here is to rapidly provide standards that leverage the innovations of all the member companies to provide an open standard that's going to help the growth of the AI industry for scale-out networks. So let's take a look at a basic pod. It's generally created with a set of racks. The scale-up interconnect shown in blue will connect something on the order of 1 to 4 racks, depending on the size of your rack and your physicals. Okay? This is a simple load store model interconnect. You know, it's got low latency, very simple routing, fixed packet size, and it's tuned to deliver these small packet sizes. You know, this network does load, stores, and atomics, as if you were just talking to memory. Okay? That will scale, as we say, up to a few hundreds of accelerators in a pod. Okay, when you need to get larger, we're going to step up to ganging these together using a scale-out network like Ethernet, of course, which is designed to deliver larger packets. It has much more complicated routing. They're variable size packets. You know, it's not designed for small, low-bore, load-store atomic operations, okay? But it does scale to a very large thing. So if you combine the two, you get a UALink pod. You know, as I say, the UALink network is designed for low latency. It's a very optimized protocol for high bandwidth. It's lower power. We don't have to have nearly as much complex buffering or, you know, packet processing or holding as you would in a scale-out network. And it gives us a much lower die area at the end of the day. So what does the specification give you or talk about and define? You know, the UALink Interconnect is going to be designed to describe accelerator to accelerator communication in terms of loads, stores, and atomics. You know, the initial focus is about sharing memory between these accelerators, allowing one accelerator to access the HBM memory of another accelerator, and so on and so forth. This allows you to spread your models across multiple GPUs in your rack. Okay. Again, the unit of currency and the things that are defined are going to be load, store, and atomics, or as they're called on the bus, read, write, writeful, and atomic operations. It's very simple load store semantics. It is not fully coherent. It is software coherence. This is not a particular impediment in this space because GPUs are used to this sort of thing. This is how their software is built. It's also really, really hard to get people to agree on a coherence protocol. So initially, this is not coherent. You know, the specification taps the experiences of that large collection of promoter companies in building these sorts of systems. And it's seeded with, you know, fabric technology from AMD's Infinity Fabric that's been proven over multiple generations and run in multiple servers. So this is not, the foundation is a very tried and true set of protocols and technologies. So if we look at the picture here, I wish I could point better, but you know, on each side, we're going to have a node, which is going to have a host processor. That's going to typically be the x86 of your choosing or an ARM core of your choosing. You know, there's going to be a local coherence mechanism and protocol to attach the host and some number of accelerators. The host has its DDRs and HBM memories. And then the accelerator across UALink can go through the switch to talk to the different accelerator's HBM memory through loads and stores. So it can issue loads and stores directly through the switch over to the other system nodes and vice versa. So what are the benefits? As we said, it's low latency and it's high bandwidth interconnect. You know, it scales to hundreds of accelerators in a pod. Now, we feature the same raw speed as Ethernet, right? We're going to use their SerDes and we're going to recycle, you know, all that proven SerDes and cables and connectors and retimers and all of that machinery. But we're going to replace the protocol stacks above the physicals with protocol stacks, you know, layers that are custom to UALink that are lower power, less complexity. And the goal is to achieve a similar latency to PCIe switches. You know, the simpler, you know, the theme again is simpler and simpler as far as the packing, the protocol, the routing. That simpler stack gives us a lower power, a lower cost, and the bandwidth lowers our TCO. But more importantly than that is this thing is open and standardized, right? So we can harness various techniques and innovations from other companies and drive new features into it and meet a variety of needs to give us, you know, an interconnect that's going to enable interoperable components across an ecosystem. You know, again, we leverage the ubiquitous Ethernet infrastructure. So now that was the introduction. So now we'll go into a much more technical, you know, bits, bytes, feeds, flows, protocol section. We'll look more at those protocol layers and the machinery involved. Okay, so we'll start at the bottom, right? Again, Down there at the bottom is your Ethernet physicals, right? This is standard 802.3DJ layer 1 physicals, right? Straight out of the Ethernet box. We're using a standardized forward error correction or FEC error correction protocol. We'll talk more about the details on that in a minute. We've got low latency. You know, in the protocol, the way we stack the code words inside to help them line up with our custom TL flits to help lower latency. This is a lot of low-level details, and I'm not necessarily the expert at this. But in general, we've made minor touches and tweaks to the Ethernet standard here that are specific to our world but are compatible with the physicals. It's 200 gigabits per second per lane nominally. We support 100 gigabit per second lane, you know, half speed mode. As I said, the FECs are standard and the physical layers. You know, 4 lanes are defined as a station. Each lane is 200 gigabits per second. That's right. And you can have 1 to 4 lanes within a station in bifurcation. So you can get up to an 800 gigabit per second port, 400 and 200 with by 2 and by 1, or by 2 and by 4 bifurcation. Okay, so that's your basic physicals. That's the foundation on which everything rides. You know, we move up to the next step, which is going to be a data layer and a transaction layer, or a data link layer first. The data link layer supports, you know, these are fixed payloads. It's going to be a 640 byte flit at the data link layer. We're going to add 40 bytes of forward error correction and overhead to that to get a 680 byte code word down at the physical Ethernet layer. These flit sizes are fixed. They do not alter. They do not change. Okay? One layer up is TL. When we get to that in a minute, it's got a 64 byte flit. Its size also does not change. The protocol is wired for or provisioned for up to 4 virtual channels. And UALink 1.0, the switches treat those as a single channel, but the provisioning in the machinery is there to handle 4 virtual channels. The data link layer here above the physicals handles link level retransmission to handle errors and replay for errors, so that machinery is handled inside the hardware. The software or the higher levels of the protocol don't have to manage that piece. That's handled directly in hardware. We do credit-based flow control everywhere. There's a credit-based, you know, there's a crediting scheme at each of the layers in the stack in the protocol to move packets through that layer of the protocol. We provide same address ordering to a 256 byte boundary. So accesses within any given 256 byte region stay ordered naturally. If encryption and authentication is enabled, everything stays ordered, but that's a slightly different mode. But in general, it's 256 byte ordering. You know, we're targeting low latency operations. So cable lengths of something under the order of less than 4 meters, request to use times of 1 microsecond, again, 1 to 4 racks, and endpoints in the neighborhood of under 1K. Okay. We allow requests and responses for multiple source destination pairs to be outstanding at the same time, and we pack them together in flits. So multiple destinations and sources are packed into a single flit. We'll see more of this in a minute. Finally, we have end-to-end authentication and encryption. So we support confidential compute. Let's see. So now that's the data link layer. If we move up to the transaction layer takes commands from the protocol layer. The protocol layer is a very flat interface with several channels we'll see in a minute. The transaction layer takes that, packs them into 64 byte flits, both data and header flits. And then they're pushed through the data link layer to get transported across to the PHY, across the wire to the switch, and from the switch onto the destination accelerator. You can see the security layer here above. That's where the encryption occurs before you enter the protocol layer and runs end to end all the way to the other side to the protocol, the encryption on the other side past the protocol layer. You know, and then the applications OS drivers and the accelerator right on top of this. So let's look at a UALink interface stack. The workloads in these sorts of AI scale-up require symmetric access between accelerators. So each interface stack to 4 ports has on the right here a thing called a UPLI originator and a thing on the left called a UPLI completer. The originator for this port is how the accelerator issues commands, issues reads, writes, atomics. That flows through this stack, through the switch, through a stack on the other side, and is responded to on the other side at a completer. So the completer you see here in this accelerator is what's receiving requests from all the other accelerators and responding to them. The originator is driving commands out through to the thing. So it's a bidirectional symmetric interface. Inside of each one of these interfaces, there's going to be 4 channels. There's going to be the request channel. That's the channel that we send our reads, our writes, our atomic commands out. When we send a write command out, we also use a request data channel. It's called a rig data here. And that's the write data. So if you issue a write, data comes with that write request. Okay? If you issue a read, it's just a request. The read is going to return on the response channel. For the data for a read returns on the response channel for that read. So we have a request where we send all of our commands, and then we've got 2 response channels, a read response channel and a write response channel. Okay? So the originator issues the requests to other accelerators, the completer receives those. So the originator on this side will issue the request, the completer on the other side will process it on the other accelerator. It'll send the response back, and it will flow back up through these blue arrows into the originator on one or the other of the response channels. We have a 57-bit address that is provisioned for multiple address spaces. This allows accelerators to be very flexible and have differing address schemes as they see fit. We don't specify that in the specification. The routing of the commands is totally driven by the request from the source accelerator. There's a destination accelerator ID field that's provided inside the request that routes the request down to the final accelerator. As it says here, the same address is ordering for the request to 256-byte boundaries. The completions are unordered. Oh yes, a confidential computing, we encrypt on 3 different channels. We encrypt on the request channel, the read response, and the write channel. They each have independent counters that manage the encryption on each channel. So we start at the top here with our completer and originators, and we go, that's just a flat interface with command beats that drive all the command information in. The TL flit is going to pack that there into TL flits that are each 64 bytes and always 64 bytes. Then from the TL is going to issue that to the DL. The DL is going to take up to approximately 10 TL flits and pack that into the 640-byte flit for DL that goes to the PHY. The PHY takes it and packs another 40 bytes on it to give you a 680-byte code word at the end of the day. So let's take a look at a transaction layer flit. So TL flits are organized as 16 4-byte sectors left to right. It's divided into an upper and a lower half flit of 32 bytes each. Right. The control flit is used to issue requests, read responses, and write responses. The other flits, the data half flits, which are shown here in blue, are the data for the given requests and responses. So, for example, on the left side here, we have 2 write requests. They're full write requests, so they don't need any byte enables. And write request 0 on the right, his data fills in after request 0, then request 1 comes after it, and his data fills in, so it goes right to left from what was in the control flit, filling in the data until we've exhausted all the data, and then we do another control half flit. Control half flits are required to be in the lower half flit. This is a simplification. We don't want you to have to replicate decoders in both sides, just one set of decoders, not both sides. So when we get down here, you'll notice this data 7, which was the last half flit for number 1, would have wound up in the right, but since it's the last one, we slide that to the left, we put the control half flit in the right side. The green things are commands, the responses, which take, the responses are orange, and the flow control packets are 0. So basically on here, we're going to have requests, we're going to have responses, and then, yes, the one thing here, the yellow one, is a flow control. That's how we hand credits back or issue no ops if there's no traffic to be had. Requests and responses can come in a variety of forms. The uncompressed request is 4 sectors, 16 bytes. You can compress that down to 8 sectors. If it's been used before, we'll cache the, some portion of the address bits and some of the information is cached or reproduced, so we can fit it into a 4 byte. So once the thing gets going, you're going to see, you'll go down to compressed requests, which we'll see over here in a minute. Those take 8 bytes. Uncompressed responses take 8 bytes, 2 sectors, and a compressed response is 4 bytes. The uncompressed, virtually all the responses are compressed. The only time a response is not compressed is when there's an error. Okay? So to get an idea of the sort of efficiencies we can reach, right, we can go up to 256 byte writes. So the example on the right shows the max efficiency case, which is 3 writes packed in with 2 responses, followed by 2 requests, followed by 3 responses and 1 flow control packet. The rest of that's data. Add all that up, the efficiency is 95.2%, right? You're doing a whole lot of data for not a lot of control. The high efficiency example, when you can't use a compressed request, drops to 92.3 as shown in the figure over here. So not a big drop. So that was a TL flit. Let's go look at a data link layer flit. This is the next step down. After we've got the 64 byte flits, and we're going to pack up close to 10 of those into a data link layer flit to send off to the PHY to issue out to the link. So we started a 640 byte DL flit. Now, all of these things have some overheads that we have to account for. The flit header, which is the green thing down in the bottom left corner, that takes up 3 bytes. Segment headers, each of these red circled box things are called segments. We need 1 header control field in there to tell us what's in that segment. So that'll take 5 bytes. We need a CRC at 4 bytes. So that, that knocks us down, 12 bytes here. Okay? So the efficiency of, the inherent efficiency of a data link layer flit is 98.125%. Okay? And as TL flits go into the DL flit, they're actually, as the designer of this likes to describe it, they're poured in like water, right? So we just fill in the bytes. Those are the blue bubbles. We fill in the bytes as we can. And when it breaks, it just picks right back up there on the TL flit stream for the next DL flit, right? So it does not waste bytes. Okay? This is a 640 byte DL flit. We've got to add 40 odd bytes to forward error correction to that with some additional control information a bit on the side. And that gets us up to 680 bytes. To cover transmitting the FEC overhead and things, we actually run it at 212.5 gigahertz or 106 point something for the 100 gigahertz case. Inside the data link, right? We've got the TX packing, that pouring the TL flits into the water like water. And rate adaption, we've got valid backoffs. We've got a messaging service between the DL layers to allow them to trade control messages between each other to manage the link up downs, rates, things of that nature. That's part of what the segment header does. And then, of course, we do the flip packing, the link level retry. Again, 802.3DJ physicals. All right, so let's look at a scale-up pod here for a minute. UALink 1.0 tries to be simple, so we've limited it to single-tier switches right now. So the number of switch planes, to manage, if your given accelerator needs a certain amount of bandwidth, you manage that by adding more ports to your accelerator, up to whatever you need to meet your needs and your requirement for bandwidth. Okay? every port you add to an accelerator adds another switch to the system. So each switch connects to each accelerator, but only once. So there's one path from a given accelerator to a given switch. That's just the hardwired into the topology. Now, because of that, the number of switches you have, the radix on your switch bounds the number of accelerators you can have in your pod. So if your switch is a radix 64 switch, you have to connect from the switch to everybody. You can have 64 accelerators in your pod total. Okay? So, that's the basic connection. Now, we show an OS domain or a node here, a host, the accelerators. The number of accelerators in a host, your configuration of your nodes, that's, of course, up to you. But the accelerators, you get lanes, links, and each link goes down to the switch, one to each switch, and the radius of the switch tells you the number of accelerators. All right. You can take this system and break it into virtual pods. You can take some number of accelerators and isolate them off by themselves as a virtual pod, and that keeps anybody else from talking to them. Routing tables and protections in the switch isolate the virtual pod to itself. Okay? And, once you've done that, the errors in a virtual pod shouldn't impact, are designed to not impact errors in the other pods, right? You should be able to recover errors by resetting stations and ports individually in the software, in the management software. We'll see the management software a little later. Now, there are certain catastrophic errors in the switch that might require a switch reboot and a restart. Okay? But in general, we try to isolate errors down to virtual pods and prevent, cross-contamination. So this slide is going to talk about why did we need, we've got the Ethernet physicals. Why can't you just do Ethernet-like protocols on top of it, right? And there are a couple of facts that are going on inside an accelerator like this. The first thing is the accelerators have a lot of HBM memory. They have a lot of channels to that memory, and they're going to interleave on very fine 256-byte granular boundaries to allow the different accelerators the maximum bandwidth into their HBMs. Okay? So that's going to tend to drive very small bore communicate to that. If we want to extend that, right, we really can't afford to be building up a large packet around every single load. We can't afford to try to group traffic from one accelerator to the other all in one packet and wait for that data to come, because the accelerator is going to continuously communicating with multiple accelerators. So what we do instead is we're going to pack the requests and the responses for multiple source destinations in one TL flit. As you saw back here a minute ago, these requests can be headed to different destinations. So the TL flit gets built at the TL on the accelerator going towards the switch with a variety of packages to go to different destinations. It hits the switch. The switch unpacks those things in a very regular way and sends the various pieces to the egress ports that you need to go to. Now, by the time you get to the switch, there are a number of accelerators on the sourcing side that are all symmetrically spraying traffic to all the other accelerators. So on the far side of the switch, you're going to have enough traffic coming in from all the different accelerators to, again, build up a full flit of stuff headed towards the destination accelerator you're looking for. Okay? So this is kind of a fundamentally different sort of mentality and structure than you might see in Ethernet. Okay? So we pack and respond them, and get them to multiple destinations. That's a fundamental difference, and that's kind of the key to how this interconnect works and gives us our low latencies, our simplicity, and gives you that fast latency and turnaround time at low hardware complexity. Okay. All right, so let's talk about system management. It was important when we were putting this together to have a way not just to think about the interconnects itself, but how a way to figure out, how you were going to manage and deploy all of this technology in a reasonable fashion. We wanted to provide you the right mechanisms to control all the components in these pods. So what we've done is we've come up with, a flexible management model. It can be more like Ethernet if that's what you like or suits your purposes. It can be much more lightweight, like a PCIe switch model. Okay. The picture I'm showing here is one embodiment. It's a representation of how you can do this. It is not the only way. It's certainly a reasonable way to do things, but it's not the only way. There's a lot of flexibility in here. So if we look at this figure, on the bottom, we've got those accelerator nodes we were talking about earlier. We've got CPUs hooked to various numbers of accelerators in an interconnect. They each have NICs, possibly in BMCs, to talk through a network up to the pod controller at the top we'll get to in a minute, right? This is your standard compute tray, right? That purple box in the middle is sort of an abstraction. That's the agent manager. That's software, right? So it's not really hardware, but it's drawn there abstractly as software. We define interfaces. We don't define where they run. We give you common interfaces and common workflows and APIs, but you can run them where you need to run them. If they need to run on a CPU, they run on a CPU. If they run on the BMC, they run on the BMC. We don't mandate that sort of thing because, many different companies have legitimately different opinions on how that needs to be done in their scenario. So we describe these more abstract constructs in agent manager. The agent manager on the node, is responsible for things like setting up the accelerator, turning on the accelerator's links, putting an accelerator ID. We talked about earlier, the routing is done by accelerator ID, putting the accelerator ID into the accelerator. Okay. So if we then, so those are the compute trays. If we go up to the switch platforms, these are going to be your switch trays, right? They will also have a BMC and a NIC probably. They'll also likely have a TPM module for, trust and authentication, although that's not required. This is just a representative sample. And then, of course, there's going to be a processor that executes the switch tray or the switch agent, switch manager, okay? Now, that's going to be responsible for setting up switches, turning on switch links, configuring registers in the switch. Both of these purple agents, work on behalf of what's called the pod controller. The pod controller is the entity, the construct at the top that manages the entire system. Okay? And the pod controller talks to the agents in the compute trays and in the switch trays, telling them what to do to manage the overall system. Okay? This works through a series of APIs and communication. This is a framework that you fill out and you build out when you build your particular pod solution. So let's look at that a little more closely. We've got the pod controller up there at the top. That's running who knows where. On the left side, you're going to see we use a technology called Redfish to provide a standard way to connect have the pod controller software through a set of APIs talk to the node management agent. Redfish is very standard, very common in servers. The guy who does this for a living tells me that every server has one of these. It's a RESTful API. It runs over HTTP. You can just think of this as the language that the pod controllers use to talk to the node management agent. When you get into the node management agent, the interconnect from the node management agent software to how the accelerator is built is entirely vendor defined because that's going to be specific to the vendor. Okay? On the other side, the pod controller talks to the switch management agents through a technology called GNMI. GNMI is apparently very common and very familiar to Ethernet and folks. So they use that. It's, again, another interface, another protocol for handing data around that's very common and familiar. So that's how the pod controller talks to the switch management agent software. The switch management agent then talks to the physical switch through something called the UALink switch abstraction interface, the SAI. So what that is a set of API calls or system calls that you fill in. There's APIs that say, this is the function we want. You fill that in with however it takes to make that work for your physical switch. Ethernet has a very similar concept, but it's important to note this is not taking the Ethernet SAI and extending it. That turned out to be technically infeasible. So instead, this is a SAI that's purpose-built to do this job and work for this. If you're interested in this sort of thing, there's going to be an in-depth talk on the management interfaces at the San Jose OCP Global Summit in October 2025. So there'll be a lot more you can learn there on this. So this isn't holding still. We continue to change. We continue to add things. The specification we released in April was for the 200 gig, Ethernet physicals. So the spec covers everything from the protocol layer all the way down to the physicals and back in one spec. Eventually, here in a few weeks, we're going to split the specs and we're going to take the protocol and the TL layers and the layers that don't change with your physicals and your DLs, and we'll split that into an independent spec that'll stay the same no matter what your physicals are. We just released a PCIe specification, a PCIe flavored specification for the DLs and the PHYs into IP review, and that'll be released sometime soon. The Ethernet one is the bottom half of the current specification, and that'll get turned loose as its own specification when we crack the specs apart. So we're going to have the ability to support both types of physicals, and the protocol and the TL stack above it will remain the same. Another thing we're looking at adding is something called in-network collectives. An in-network collective is a way for the switch to offload processing from the compute units, from the accelerators. A set of accelerators agree to work together. Their individual ranks. They each have input buffers and output buffers, and various collectives will, read from all the ranks, reduce the data on the switch, do the arithmetic, and then write all the data back to all the switches, and that happens all off-board on the switch, so the accelerators aren't tied up doing that job. Spec for that is expected to be released in 2025. There's an initial start of that internally, but we'll have the final spec out in 2025. We're also looking at doing 128 gig and 200 gig UCIe PHYs and chiplets. That's under development. The figure here is tentative. Exactly where the cut line is between UCIe and the accelerator and where the TLs go, and some other details are being worked out, but it is definitely coming. All right, to summarize, so UALink is out to address a demand for an open industry standard scale-up interconnect for AI applications, right? It's a direct load store model, which is significantly faster and lower latency. It's open standard. You can participate. Many people do. We leverage all the best technology we can get from everybody else. And it advances large AI training and inference. Scales to hundreds of accelerators in a rack, and you can find the 200G specification on the internet. Web search for UALink Consortium will get you straight there. So, thank you. And yes, now I'll go back to the Q&A slide and let people ask questions. I think there's a mic. I hope that's a mic. Excuse me?
How UALink saves energy and how much? How much power it saves and how you achieve it?
How does UALink save energy? Well, like it said in there, right? Other interconnects, you're going to have a lot more buffering. You're going to have a much more complex set of logic to manage more complex. Not to pick on Ethernet, but to pick Ethernet, right? Ethernet's got to have a lot of variable size packets. It's got to have a much more complicated routing. Ethernet routing isn't done in a 10-bit identifier field with a fixed route. Now, that's fine and that's fair. Ethernet has to do a lot that we don't have to do. So most of our energy that we're going to save is going to be from throwing out a bunch of things we don't need in the narrow universe we're in, or the narrower universe we're in, where it's just load store through a fixed one level switch to targets that are identified by a 10-bit ID, right? So a lot of that machinery that a more complicated scale out network needs to do its job, we don't need. I mean, we're a hammer, that's a screwdriver, right? You need both tools, but pick carefully and use the right one. That's an interesting question. I don't know if
that would be very important for going forward in the AI application.
UALink doesn't say what's in that box called accelerator.
Okay.
Right? I believe we don't necessarily try to access this. We try to access just the GPU memories, not necessarily get up into the DDRs of the CPUs. But that's a choice we've made.
Okay. But in the future, you may want to see unified memory.
Well, I don't think we stop you from doing that. We're going to deliver reads and writes and atomics to your doorstep. Okay. And you're going to do what you do with them. And if you can do that without deadlocking, go with God. Okay. Right? We're not going to tell you no.
Okay. So there's nothing preventing doing that.
Other than complexities in your coherence protocols or things where you might have trouble, no. We don't spec that. We just say, here's the load, here's the store, here's the atomic. Get us a response back when you can. So if you have a coherent fabric behind that and you're actually trying to talk to the CPU's memory, that's fine. Now, we do not support, and will not support anytime soon, a coherence protocol where probes or snoops move across the interconnect. We don't have those commands or that complexity. Now, UALink does provide vendor-defined commands, and if you can make it work, again, go with God. We won't stop you. We can't. But that's not what we're targeting or what we specify.
Okay. Thank you.
You're welcome.
Yeah, my question has to do with checkpointing. That with these, especially with this LLM runs extending way beyond the MTBF of the underlying hardware, that checkpointing and restarting function. With this fabric, is it expected to be managed by a centralized unit? Is each processing node going to be responsible for doing its own checkpointing out over the fabric?
Well, okay. Good question. Can't say that I can answer it definitively for you. There's nothing in the specification that talks directly about checkpointing. Okay. So that's going to have to be a function in your software above. That's a user level program function by definition on some levels. The user level program is the only thing that knows what to checkpoint, where to save it, where to restart from. The exact machinery of how you take an error and checkpoint on that. Right, there's going to have to be and will be defined interfaces that's coming in the management section on how that we get that error reported back up to, say, operating systems or whatever software is on there to say, hey, something bad happened here. Yeah. You need to roll back. But again, since we're trying to span a number of companies and a number of people, we have to be a little careful about being too prescriptive about that sort of thing.
This is essentially a memory semantic interface. If you have a block that is intended for checkpointing, that's essentially a higher level function, and the fabric is not going to really even know what you're. The
fabric will have no idea.
Okay.
If we attempt to have any idea, we're inevitably going to annoy more people than we're going to help. So it's best that we stay out.
Add latency. Yeah.
Yeah.
Okay.
UALink right now is being framed in response to Ethernet primarily, but what about like the scale up Ethernet Lite type of initiatives that are happening? How would you describe the differences in philosophy?
Well, I think,
strategy?
You're asking me a business and a political question. I'm a technical droid. But, I believe that UALinks, we really are aiming at scale up, not so much Ethernet. This is scale up.
I mean from a technical perspective, because the UALink having, the smaller buffers, et cetera, but then scale up Ethernet, the protocol doing similar things, having the network collectives already, like from a technical perspective, you're comparing it to, Broadcom pushing the SU.
Well, I'm not going to really get into talking about other competitors' products in this context and in this venue, but I will say, if you ask me what does this most closely look like to me, it's more like NVLink.
Yes.
Maybe it is related to what he was talking about. Broadcom has SUE, Scale Up Ethernet.
So I'm told.
So we have two different efforts. How we can combine them, or
well, I will say that yes, they have SUE, but I will also say, like I said before, there are hammers and there are screwdrivers. And trying to make a screwdriver be a hammer or a hammer be a screwdriver isn't necessarily the best thing. I believe there's places for both types of techniques here, and it's a false choice to say we need to only have one or we're going to combine the two.
Does UALink take advantage of Ultra Ethernet Consortium specification? Or
No.
different? No.
Other than the physical layers, obviously. We shamelessly use the physical layers.
You said that you may support the PCI PHY. So,
Yes.
currently only supporting Ethernet PHY. So, do you have a plan to support other kind of PHY, including
Yes,
PCI?
yes. We're going to be releasing a specification for PCIe-based PHYs, fourth quarter there. It's in IP review now. It'll be out soon. And we, of course, the current one is based on Ethernet PHYs.
So,
Those are the only two I'm aware of.
Yeah, currently all the GPU has only PCI interface, NVLink, whatever. And the reason why you trying to support PCI is legacy, trying to support the legacy GPU interface. GPU has only PCI interconnect right now, right?
I believe. Is he talking about 100 there?
No, GPU is connected at the PCI, host interface. All the GPU, AMD GPUs.
Thank you for the great presentation. So it appears like the journey for UALink is similar to CXL's journey, essentially. Go from PCI to CXL. This is going from Ethernet to UALink.
I'll take your word for it. That was
right.
before my time.
So the question is, what key differences do you see between CXL and UALink? Could they coexist? What are the different ways?
I'm sure they can coexist.
Mm-hmm.
Nathan went up to, I started working at AMD in last February, and I haven't touched CXL personally. Okay, that's new work. It's concrete's fairly wet.
You're going to support that in December's the release, right?
Spec will be coming out in December if I lose enough
Are you going to
sleep.
support all the MPI productive communication protocols?
No.
Only subset. Do you support the scatter gather? No. Only the reduced or reduced.
Broad for a fully offloaded. Okay, I assume we can talk about this.
we can. Why don't you go ahead?
Okay, so the short answer is the intention is to have what I'll call collective primitives, which are a load reduce instruction, a store multicast instruction, and an atomic multicast instruction.
Right.
If you use those, you can build any collective you feel like building to your heart's content.
Right.
Okay. We will not be supporting the full. We also intend to have a block offload mode where you can send a control block to the switch, tell the switch, go do that collective, send it a control block with all the addresses, the links, everything you need to know about that collective, and the engine and the switch will just do that work for you and then get back to you and write, a status back to memory when it's done. Okay. For a block offload collective, we're going to support 3. We're going to support broadcast, reduce, and all reduce. And the reason we need to do that is those are the only 3 primitives where every rank is the same. Okay. And the other primitives, the other ranks are different, so you then have to start knowing which rank is which number.
Yeah.
And if you have 1024 of those things, you're going to need 1024 times the rank numbers worth of bits and a big long list to tell you what to do, and that becomes untenable and unmanageable. So we've made a very deliberate decision.
So you want to make sure the processing is very simple. in the switch, right? It's done in the switch.
Yes, the switch will have a, load reduce, aka reduce and all the reduce and all reduce collectives. The data gets run through a reduction function.
Yeah.
Whatever that winds up being, add, min, max for whatever data types. Probably not block scalar because that's hard. Because the block scalar data's over here and the other data's over here, and that's problematic to implement. It's not impossible, but it's hard.
Yeah.
Right. But that's the limits of where we are right now in our thinking on that. But I don't ever think we're going to be doing offload of anything but those three, full offload of anything but those three primitives, because it just becomes an untenable mess to deliver the control information to the switch.
Agreed, yeah. So in terms of distribution of the function, so that's going to be all done in the switch. And anything we need to do in the GPU side?
No. Well, I mean, your accelerator has to issue, you have to issue the appropriate commands.
Okay.
Right? If you want to do you can't just say do a load and expect us to realize that's a load reduce. So you're going to have to spit out the appropriate bus opcode.
So that can be done in software.
That's up to your accelerators, and whether it's software. Some people do it by adding new ISA instructions. Some people do it by,
But you will add
having page table entry.
Protocol, you have an indicator. You can provide the indicator.
Yeah. There's a new command type.
Okay.
For the load reduce. The load reduce, store multicast, atomic multicast, there's new command types. And then there's a different command type. UPLI has a concept of something called a write message, where you can deliver just a payload of data up to 256 bytes.
Yeah.
We use that to deliver control blocks for the full block offload engine type work. Or at least that's the intention right now.
Okay. Great.
All of that's subject to change until the spec comes out. There are people who disagree with me.
Looking forward to it. Thank you.
You're welcome. Sure. I don't think it will be your last, but...
Yeah. So does the switch support link aggregation?
Link what?
Does the switch support link aggregation? Combining multiple links and makes them look like one virtual big link.
We can, the stations support bifurcation, but I don't think we do. We don't do that dynamically, I don't believe.
Okay.
Next.
From the fault tolerance perspective, and the failure handling, will the spec mandate like the link failure handling or the multipathing or the internal protocol handling?
The spec already has a section on RAS. Okay, and when you take an error, like parity error on the internal interface, we have a notion of what we call the drop mode. Right, where the guy who detects the error immediately curls up, in the fetal position and stops sending traffic through, so more errors don't propagate, and then that communicates up to the pod controller, up to the switch agent and the pod controller and so on, to say, hey, there's a problem, and then of course it's a vendor-specific recovery sequence to get out of that. But the underlying hooks to know you've had a problem and to feel that problem are there. We leave the rest of it to the design and in the configuration stuff. The configuration spec that's coming out later in the year will probably have a little more on that. But it's we don't hard prescribe anything we don't have to.
Okay. And is this, will this feature be, like the RAS features would be optional to the manufacturer or the implementer, or?
I don't think that's going to be completely optional. The compliance story is still being written.
Okay.
Right. So exactly what's going to need to be there to be fully compliant or not, that's a different work group, and they're in the middle of figuring all that out for us.
Okay, great.
Yeah, I mean, having RAS isn't optional, but exactly how far and how it's handled is,
okay. Thank you.
Open to some definition. All right. Guess that settles it. Everybody have a lovely lunch.